Good morning. We've had some excellent presentations regarding fixation of press fit caps and threaded caps, and it is my belief that fixation of uncemented caps is solved. So what we're left with is the actual bearing. Now, we've also heard about polyethylene wear and osteolysis, and this has led to a great degree of variation in the bearings used, particularly over the last 5 to 10 years. It's also led to a lot of hard-on-hard bearings being used. Now, in the UK, we've had our tails stung a bit using large metal-on-metal bearings in a conventional hip replacement setting. Therefore, there's been a large swing back to the use of hard-on-soft bearings. Because of the issues regarding cobalt chrome, because of worries about scratches and scratch characteristics, there's been a great deal of interest in ceramic on polyethylene, in highly cross-linked polyethylene, and in particular the use of a new ceramicized metal in combination with polyethylene. And that's what Verilast is. Verilast is the trade name for oxinium on highly cross-linked polyethylene. So if we look at how to maximize longevity with highly cross-linked polyliners, we believe that treating the polyethylene by gamma radiating it can reduce free radicals, could reduce oxidation and improve wear characteristics. We also believe by using a ceramic surface in combination with polyethylene that wear rates can be reduced, in particular volumetric wear. Therefore, the ideal femoral head must be smooth, polished and resist scratching. It must also be safe. It must be not susceptible to fracture and catastrophic failure. Also, the materials given off by the bearing as it wears must be relatively inert. And that is why we believe that the metal-on-metal saga has been, because of the inflammatory nature of the wear particles. We've talked about the design of acetabular shells, and new designs of acetabular shells, in particular press-fit shells, may increase the durability of the highly cross-linked polyethylene. So, Verilast is the combination of oxinium on highly cross-linked polyethylene. What is oxinium? Oxinium is a metal alloy. It is not a ceramic. The metal alloy is heated in an oxygen-rich environment, which converts the surface of the metal to a ceramic. Therefore, the ceramic, as you go deeper into the substance, becomes increasingly metallized. There is no layer, it is not a coating. Therefore, there is nothing to delaminate. Because it's a coating, it can bend and flex with the metal. The surface is very thin, and that's led to some worries again about delamination. However, as I've said, because it's a graded substance, the risk of delamination does not exist. So why use oxinium? Ceramic is a reasonable product. The new BioLock ceramic is meant to have low fracture rates. The advantages are that oxinium can behave somewhat like a ceramic in that it's wettable. It can be lubricated like a ceramic but does not fracture. And it does not squeak like some of these ceramic-on-ceramic bearings can. So, again, a very dramatic picture showing how ceramic fractures. What it demonstrates more than anything is when ceramic fractures, it fills the joints with these tiny, very hard materials which can lead to enhanced third body wear. So, once a ceramic, always a ceramic is how people say it. We have to revise to another ceramic bearing with all the problems associated with that. Also, because oxinium does not contain any of the common metals believed to lead to allergy, we believe that it is a safe material in terms of metal ions. Nickel allergy has been demonstrated in a high proportion of well-functioning and, in particular, poorly functioning implants. I won't talk about cross-linked polyethylene, but we all know that gamma radiating it can reduce free radicals and improve wear characteristics and improve shelf life. To talk about cup design, the first generation designs, the polyethylene was poorly congruous with the metal shell itself. The locking mechanism was less reliable. often led to failure at 8 to 10 years. Also, the lip of the polyethylene spreading across the periphery of the cup led to a thin area of polyethylene that could chip and scratch and delaminate. With the third generation of particularly press-fit cups, the polyethylene sits within the shell as a whole. It's far more congruous, hopefully reducing backside wear, and there is no thin lip which can fracture and delaminate. So if we look for evidence of oxinium, it's a relatively new product. Therefore, what we have is a collection of short and mid-term results. First of all, we want to make sure, because of our metal-on-metal concerns, that it's a safe bearing. And a clinical study undertaken in Canada, they call it mid-term. It's short-term, really. It's 2 years looking at the clinical scores comparing chrome cobalt and oxinium. And as we'd expect, there is no difference between chrome cobalt and oxinium in the short 2-year term. We can, however, use this as support for using the bearing in that it's a safe bearing. We do, however, know that oxinium, although it behaves like a ceramic, can scratch. And studies have looked at the surface roughness of oxinium following retrieval, both in vivo settings and in vivo scratch settings. They have found that oxinium is stable, but can increase in roughness. One important study that's much quoted is an RSA study from Perth. And this looked at an RSA study of, in particular, chrome cobalt and oxinium heads in combination with different types of polyethylene. What they found that with the modern, highly gamma-radiated polyethylene, the wear rates are extremely low, and in particular they concluded that with oxinium, the wear rates at 1 year were undetectable. So the summary was that the wear rate was very low. The combination of highly cross-linked polyethylene with ceramic oxinium heads looks very promising. This was not a randomized study, and they supported the use of polyethylene against ceramic or oxinium. Again, studies have looked at chrome cobalt being damaged and oxinium being damaged. And what they have shown is that chrome cobalt scratches in a far more damaging way. Oxinium, when it scratches, forms buried scratches, and it's believed that a scratched oxinium head will behave much like an undamaged chrome cobalt head. Again, evidence for its continued use. And this again is showing that the wear simulator study showed similar between a damaged oxinium head and a new chrome cobalt head. And this is again because the scratch profilometry is advantageous. One thing that we concerned about is that the wear particles given off may be different with a ceramic on poly or oxinium on poly. And synovial estimations have shown that the wear particles are the same. However, if you look at the results, there is no difference in this mid-term study between chrome cobalt and oxinium with polyethylene and a knee replacement. Again, you would expect an implant with improved wear for these advantages to be shown in the long term rather than the mid-term. But this would be evidence for its safe use in the mid-term. Again, the Australian registry results are much quoted. It's a very compliant registry, and in the results in 2010, a new bearing surface was introduced. That is a ceramicized metal on polyethylene, what we know now as oxinium, or Verilast is the new name for that. What they found that at 5 years, oxinium and polyethylene had the lowest rate of revisions when looking at bearings, in particular over 28 millimeter heads. The graph would show that ceramic on ceramic is plateaued in its revision rate between 6 and 9 years. Oxinium between 5 and 6 years is increasing a bit. So whether that graph will increase or will remain horizontal will wait to be seen. But at 5 and 6 years, the revision rate of a ceramicized metal on polyethylene is very low. This again would support its continued use. So, if I may summarize, what we appear to know is that Verilast or oxinium on poly is a safe bearing producing wear particles which are the same or equivalent to chrome cobalt on polyethylene. We know from simulator studies that the wear rates are extremely low. We know that even in damaged heads, in the case of dislocations or impingement, that oxinium heads can scratch, but those scratches produce favorable wear rates. We know that oxinium cannot fracture because it is a metal rather than a ceramic. Therefore, it would appear, looking at short-term studies, that the use of oxinium is equivalent to the use of ceramic without the disadvantages. Thank you.